Thanks for the introduction. And my name is Gary. I'm a core team member of the Rust for Linux team. So my talk today is mainly about how different is Rust code in the Linux kernel. So I will dig deep into the technical part. But to get started, I want to also do this very initial introduction of the project. So what is Rust for Linux? So the Rust for Linux project is a project for adding support of the Rust language into the Linux kernel. So the Linux kernel previously have a single language, that is C, and now we're trying to change that fact. So there's a common misconception about what is the Rust for Linux, and some people think that we are part of a Rust project and also complain to us, why do you have a separate zulip instead of just using the language down zulip, have a channel? Well, actually, Rust for Linux is not part of Rust project. We do collaborate with the Rust project in a lot of aspects, but Rust for Linux is fundamentally part of the kernel. Although we are not focused just on making changes to kernel, we also try to make the Rust language better. So we are a project involving multiple other projects. Since February, we start having regular meetings with the Rust team, and thanks for everybody make that happening. And now, if you don't know, the Rust for Linux is a flagship project goal for 2024, Rust project goal. So we are trying to close largest gaps to build Linux kernel Rust code in unstable Rust. And this covers all aspects, including language, library, compiler, and CI. And there's Nico and Miguel talk about this in detail in the RustConf. I think the video is not available for playback yet, so you probably have to wait if you didn't watch the live stream of that talk. So Rust, the core team, have these members. You may have heard about the drama a few months back about one of the core team member leaving. It creates a lot of discussions online, I would say. But we are also, so it's a sad news that Weston leaves the project, but this year we also have Trevor Gross, who's also a Rust project member, joining Rust for Linux as a core team. So we're still trying to grow the project. One thing I've often heard from people is that Rust for Linux is moving slowly, but one thing that people have to keep in mind is that kernel programming is hard. The Linux kernel itself is inherently complex. We have a large, or maybe say huge code base to work on. I believe there's currently, I don't know, maybe 500 million lines of code in the kernel. Also, the performance matters a lot, and because we are adding to a Linux kernel at production level, and so that all the code we added to it must be to that same quality. So we can't say, oh, this works maybe this works and work in some scenarios, and that's not actually acceptable. And your normal user space Rust experience is very likely not applicable in the kernel space programming. I will cover this in detail, but for one thing, the linked list is heavily used, where it's not that common in user space Rust code. We have lots of unmovable types, and the memory allocation can fail. And we also say panic is not really acceptable in most cases. And then performance matter a lot, and performance matter a lot. And it's very important, so I emphasize it multiple times. So, and actually to go back to the Rust Linux for Linux moving slowly, we actually have made a lot of progress in the past years. Everything listed here is either has happened in 2024 or is scheduled to happen in the near future. So yeah, with a lot of changes. So now I'm going to dive into the technical part of how actually is Linux kernel code different, Rust code different in the Linux kernel. So first aspect is that we have to interact with C a lot. There's a rule in the kernel that you shouldn't duplicate your functionality, so that if something is already implemented for C, then we're not allowed to re-implement them in Rust. So we can't have a code doing both in C and Rust. So that means that very often we have to call into C for a piece of code functionality. So let's look at the pointers, right? The pointers in C and the reference in Rust. So in C, you have these mutable pointers and const pointers. We don't, in the kernel, usually use volatile pointers a lot. We model accesses as volatile, not objects. So that instead of saying every access is volatile, we say, like we have the macro read once, which casts a pointer to a volatile pointer and then dereference it. So this is more similar to Rust volatile model, the volatile read and writes, instead of the traditional C model. And so that's the C part. In Rust, we have mutable references and const references. Also have pointer types, but since using them is normally unsafe, so for abstractions, we actually want to map C pointers to Rust references, if possible, instead of using pointers, row pointers directly. And now there's the impedance mismatch here, which is the aliasing is different in these languages. The standard C have something called type-based alias analysis, so that pointers to two different types cannot alias usually, unless one of them is a byte type. Additionally, there's a restraint keyword being added to so that you can mark function parameters no alias. Although in practice, almost nobody use it. And then the kernel actually have to do a lot of things that goes against the TBAA, so that we actually turns it off globally with fno strict aliasing. And on the other hand, Rust uses reference for alias analysis that, with exceptions in both cases, that a reference to T does not alias with another mutable reference. And then a mutable reference to T will not alias with any other references. So basically, all references in Rust is like restrict pointers in C. But then there's a impedance mismatch between the alias models. Like the Rust references have stronger semantics compared to just C pointers. So we can't just say, there's a mutable the const pointer in C, and then we just translate it to Rust pointer, Rust references, and same for the mutable references. So one of the primitives we have in the Linux kernel is that we have this type called opaque, which we use to cancel out all the guarantees on validity requirement. So it's still, as a safety requirement, it still have to point to validator, but reference to opaque T may be mutated, and then I wrap it in ping because most of the types are unmovable in Linux kernel, but the mutable reference to opaque T can actually alias with other pointers, similar to a mutable pointer. So like it's used in almost all the cases where we are trying to provide abstraction over the C APIs. Like there's tasks, there's reference counting, there's a work queue, and we place the opaque wrapper all over the places so that so that we can actually create references to things that may be mutated by C. So the way we implement is that we just have a wrapper over unsafe cell and maybe on it, and then we say this is phantom ping. So currently there's no unsafe ping type in Rust. If there is, we'll move into it. But basically with the cascading of all these things that we cancel out all the guarantees. So it doesn't have to be initialized anymore. It also can be mutated because of the unsafe cell, and because of ping, the mutable reference will, in the stack of board terms, mutable ampersand mute T will have will be shared mutable instead of the exclusive mutable. So in the end, what does this type give us is that allows to expose C struct directly to Rust, but make it feel like normal Rust, not full of row pointers. So that, for example, if you have a this is the current macro will give you a task, a reference to a task that is only going to be alive within the current thread, and then you can just call like .pid to get PID of it. Despite that, so this one will give you a immutable reference, but under the hood, the task struct in the kernel can actually be mutated in like different fields can be mutated at different places guarded by different logs. And similarly, for the work queue, we have this, like you can get work queue colon system to get a reference, and then you can use it to enqueue work items into it. But it's actually a zero-cost abstraction over this external struct in C. So far we cover how we handle references, but there's also we also had to deal with own pointers. It's quite common for C code, existing C kernel code, to take a void star for storing driver-specific states, and then we actually want to abstraction to be type-safe so that they don't have to cast pointers themselves. So one of the goals for RESTful Linux is that ideally the drivers themselves should contain no unsafe code if possible, and then all the unsafety and abstraction should be handled by subsystems. So this is the kernel struct device, which is fundamental for a lot of drivers. And then you will see there's a driver data field, which is this is like the rest is owned by the subsystem, but this driver data field is owned by a specific driver and it's just a pointer. So so we need to ensure that the driver can put a type there and get it working. And different drivers may want different pointers. Someone may want box, might want arc. Some may just want an integer, and some need nothing. So that we have this type we call foreign ownable, which handles the cast between and from pointers. And then we implement for box, for arc, and for also for the unit type, so that either of this type can be handled by the driver abstractions without having to explicit cast types around. The bridges that convert a Rust struct to actually do registration in C handles the cast both ways using these traits. And then similarly, we also have to handle ownership transfer from C to Rust, because a lot of data structures in the kernel in C are reference counted, and usually what happens is that they provide a pair of functions with get something and put something. With get something means increase the reference, and then put something means decrease the reference, decrement the reference, and if it's gone, then free it using some type specific way. And then we just model it with this trait always ref counted with the two methods, and we have this aref type which does the reference counting. So if you are also familiar with Windows programming, you may see this quite similar to the COM object model. So that's a easy part to get started. And now let's move to things that get a bit more complicated. So one of the things is allocation. Allocation, you may think, it's allocate, like box nil, that's simple, right? But allocation is not trivial operation in the kernel. So first of all, allocation are not all equal. The kernel have tons of GFP flags. GFP stands for get free pages, which is like name for the initial use of these flags, but now the GFP flags have been used for all the allocator functions. And there's not all allocation are equal, because you can have different GFP flags and will control the behavior slightly differently. So, and then allocation can fail. You can have, say, you have user space program leaking all your memory, and now the kernel wants to allocate a chunk of memory and figure out, I don't have enough memory. Now I have to kill a process using OOM killer and then reclaim all the memory I have. So in that case, allocation may fail. Allocation can also sleep. Same case with OOM killer. If you have the flag says, I actually really want some memory, please try very hard to actually give me the memory, it will be able to sleep until the OOM killer is wake up, kill some process, reclaim memory, and then hand over the memory allocation to you. And of course, last but not least, allocation have overhead. So you actually want absolutely minimize allocation if you can avoid it. So we previously have use a fork of alloc. So like around 2021, we just used the normal alloc crate, and then we have a linked to prevent the non-failable allocation operation from being used. But then later we moved to use a fork of alloc with allocate cater API feature enabled, and we added a lot of try underscore functions to then those available upstream, so that it will be able to fail. And then we try to upstream all of these functions, but it gets rejected because we basically duplicate all the functions in box and vac to have a try underscore something. And it's become pretty unmaintainable if that's the way we approach things. So what happens is that we fork it, and then we remove all the features that we don't need. For example, we remove B-tree map and others which does not work with failable allocation. And then we trim down the code that doesn't need, we don't need because they assume failable allocation. And then we also end up having a custom arc so that we don't use the arc from allocate. It was suggested that probably forking is not best approach because that tied us closely to the a specific version of Rust compiler because there's so many unstable features used in the allocate. So that earlier this year we switched to using extension tracing instead, given that it's unlikely that we can upstream all our changes to alloc. And then I said we will soon remove alloc completely and use custom implementation, but actually like 2 days ago, it's now in the Rust next tree. So in Linux 6.13, we will have no alloc dependency and all the alloc will be complete custom implementation. So in order to make this work, we need some features. And fortunately, we have the support from the Rust project to have arbitrary self-types and derived smart pointer being the 2024 project goal, which empowers us to have our own alloc implementation. So you may ask why we have a arc in the kernel, because as I mentioned, even before we start removing alloc, we already have our own arc. So one thing is that there's we don't in kernel we don't usually use weak references. So it saves a bit of memory. Also, it makes some of the operation easier without weak references. And also, arc in the kernel is ping by default because we have so many unmovable types. And then always have to write ping of arc is a pain. So we just say everything's ping by default. We don't provide the get mute and make mute functions. And then also we have reference content that saturates on overflow. Because if you the standard library arc, the behavior was that on 64-bit platforms, it's assumed that no reference count overflow will happen. On 32-bit platforms, there's a check so that if the reference count overflows, the process gets aborted. Aborting is not acceptable behavior in the kernel because if you abort the kernel, then there's no way to write logs anywhere, and then you just have a dead computer without knowing what's happened, and there's no way to make your bug reports. So we absolutely want kernel to continue execution. So the kernel reference counting actually have a saturation mechanism where if it overflows, it will make sure that the reference is never freed, but it's handled by the reverse counting mechanism in the kernel. And another thing that kernel uses quite a lot is introducing data structures. So famously, double linked list. Kernel use a lot of double linked list, and they're also intrusive. So you can see this the wait queue entry have the linked list head embedded in the types themselves. So the previous and next pointers are part of this struct. And this is how usually the memory layer look like for linked list, for those who are not familiar with the kernel linked list. So that this is the head. The list head itself is part of the linked list. So that when you go around, there's no data associated with the list the actual head, but then otherwise it's there's data which you can use container of to find to go from the pointer to the linked list head to the whole struct. So the kernel absolutely love linked list. Oh, the emoji is not rendered properly here. But when you try to use linked list in Rust, people will ask you, maybe you should consider some alternatives using VAC or VAC-DQ that don't actually use linked list. Kernel uses it everywhere. When I say everywhere, it's actually everywhere. So if you only grab for the direct uses, there's 20,000 uses of linked list directly, but also embedded in different structures. Because on the previous pages, I showed that there's a wait queue, walk queue entries. For example, they also embed linked list, and mutexes and even spin loss can embed linked list depending on the config options. So almost everything make use of linked list. So why do we use linked list? The biggest part is actually no allocation is required for insertion in linked list. So like vec.push, for example, require allocating memory or potentially allocating memory if you want to do that, but it's not needed for linked list. Allocation is not permitted in lots of contexts. For example, if in interrupt handler, you often want to do as little work as possible in the interrupt handler, and you just schedule something to be done later using work queue. In that cases, you will insert something into the work queue linked list, but then you can't do, well, there are GFP flags allow you to do allocation inside atomic context, but usually you should avoid that. And so this is why allocation is strongly frowned upon if you do it in interrupt context and other atomic contexts. So the fact that in linked list no allocation is required for insertion is a very strong property. Also have O1 removal, and if you use RC, you can also have the weight-free reading of the linked list. There's also a lot of benefits. There's I believe there's the article about the too many linked lists in Rust, which also have it's very interesting. But Rust, the double linked list is not something that's very typically easy to do in Rust. So the fact that linked list is difficult in Rust is almost meme now. But another key factor is that in the kernel, the list head is going to reference itself when it's empty. The next pointer and previous pointer both point to itself. This means that initializing an empty linked list requires self-reference. It is possible to use null pointers instead of using self-reference for linked lists, but that means an additional branch instruction for insertion and deletion to check if something is null. And that additional instruction is too costly in the kernel terms. Well, usually people don't matter, but kernel people cares about that a lot. So this means that instead of having something pinged when you use it, like future, this have to be initialized to be pinged to begin with. Another thing is that ownership transfer becomes unclear because each list head can only be added to one of the single linked lists. You can't have that to be added to two linked lists. But a struct can also contain multiple linked list entries. So you can have different type of linked lists contain the same thing. So like, how can we actually model this with types? So let's look at the first question, first issue here, the ping initialization. So Rust have this ping type which work very well with async futures, but async futures are initialized normally. Like async futures need self-reference because you can have you can use lifetimes. If like you have something on stack of this async function, and then you can create reference to it, and then store on the same stack, and that will create self-reference. But for futures, because when you call an async function initially without pulling it, it's actually not. It doesn't have the self-reference to begin with, so it doesn't have to be pinged. So the pinging guarantee for futures only kick in after the first pull. However, as I mentioned previously, that the linked list head and entries themselves need to be initialized to ping to begin with. So in the very early version of Rust for Linux, we actually required all the data structure to be created unsafe and then initialized pinged. So this is an example of the mutex in 2022, where you can see we have the one unsafe here, one unsafe here, and we actually want to use it. You have to do unsafe here to actually initialize it without like to create it without initializing it, and then you have another unsafe to actually to have things initialized. Now, it was the biggest source of unsafe for drivers. The fact that we have to unsafely create something and then unsafely initialize it. The fact that things cannot be initialized to begin with. Obviously, the Rust way to solve it is macros. If it couldn't solve it, more macros. So in the end, we have this this macro, which we have. You see, we have the attribute macro, the ping data there. So we can annotate which ones should be pinged, and then we have this ping init macro. So the So what we end up having is that we have this trait ping init. So you can think of similar to future. It's just a different color. And then when you create something with constructors, it doesn't return the constructed object anymore. It returns the input of ping init, similar to an async function. It doesn't do anything. It just returns a future. It just describes how things should be initialized, but not initialize things to directly. The ping init macros is similarly allow you to construct a type using similar to struct expression syntax. But under the hood, there's a lot of magic expanded there. So you can think of it similar to async blocks, which also only describe how we should initialize the example type here, but doesn't actually initialize it. And then the actual initialization only happens when the final location is available. For example, the arc ping init function will allocate an arc uninitialized, and then go through all the call this ping init function in the ping init trait to initialize it. Bail out if failed, but if it's successful, then you get an arc that's pinged to start with. So there's no separate phases needed to create something unsafely and then initialize it later. Now, so that solves the first problem of how to create something to with self-reference to begin with. And so how do we solve the ownership issue? So here's a simple case study of the ownership transfer. So you have a type with work struct. You enqueue it. So you initialize this is the process work. It's a function pointer, and you initialize it. And then the caller must ensure when you queue the work, the caller must ensure that my work here must be alive until the process work is called. So you can think of that this queue work function actually transfer ownership to the queue, and then the callback transfer ownership, take the ownership back from the queue. So it's not that difficult. But this is the thing that we end up with. So it's actually a lot compared to the C code. So we have a type which encodes the has a relationship. So this macro will validate. We have this macro implement has work, which will validate that the has a relationship is there, and then we'll hide some unsafe implementation there. We have types that have self-references to types themselves, so that we can ensure that by having this type matching this type, so we can ensure that the pointer that you end up giving to the work queue is same as pointer as the one you take back. So the input work, the work new function, which I happen not to have on this slide, but the function pointer is initialized when you do the new work macro there. So we have this self-reference to make sure that the type actually match. And then we have the bridging code that actually expands some to extern C to actually bridge things across. And then now the ownership is simple. You can see instead of queuing a single like a walk into the walk queue, we actually queue the container itself, and then using this trait, we will be able to find which part of this my walk is the actual walk item, and then we give that to the C API. And similarly, when going back, we have the container of call also abstracted away. And then we can have multiple walk in the same struct. And the way we do it is give IDs to everything, so that if you actually need multiple walk items in a single struct, you just give different IDs. Not the most elegant way of doing things, but it works. So extending the walk queue happens to be one of the simpler cases for this kind of pattern, because queue walk on can be called safely if walk is already on the queue. So it actually internally have atomic variable to track if the walk has already been queued. But that's not true in general for linked list scenarios. If you're interested in how we solve the general linked list issue, we have you can go to rust.docs.kernel.org. We have like maybe 20 types and 10 traits to actually abstract the simple linked list pattern. And we plan to use a generalized has intrusive trait and proc macros to replace the current trait and macro implementation. Yeah, but wrapping up, this is like a normal piece of RESTful Linux Java code, right? So you have the opaque handling the difference between C, the aliasing model difference, the impedance mismatch between C and Rust. You have like traits handling ownership transfer between C and Rust. You have the arc, like this is allocation. You can see there's GFP kernel flags being passed there, so that for each allocation you can actually specify which flag you actually want, as opposed to just do a box new. And then we have the handling of ping initialization. And then we have this handling of linked list and self-intrusive data types. And then we also have some actual magic there to ensure that the line number, etc., will be can be transferred to C, which I didn't cover because I don't think I've got enough time. Yeah, so that's So this is how like normal piece of RESTful Linux code. I'm pretty sure you can agree with me that this is very different from your normal user space Rust code. Thanks for listening.
Thank you, Gary.